Next, we try to study the response of a discrete time LTI system to a non-periodic discrete time sequence and periodic discrete time sequence. We have this understanding. So for an imaginary exponential signal, the discrete time LTI system will have a zero-state response equal to the same imaginary exponential signal but modified by system's frequency response. We know that for a discrete time non-periodic signal, we can represent that signal by a linear combination of imaginary exponential signals. Due to the linearity of the LTI system, the response of the system will be equal to the same linear combination of the responses to the imaginary exponential signals. So in other words, the zero-state response actually is the multiplication of the system's frequency response and the input signal in the frequency domain. So based on this understanding, we can represent the interaction between the input, the system, in the frequency domain by this mathematical expression. Well, this part is the interaction between the input, output, and the system in the time domain. And this part is the interaction in the frequency domain. So they basically describe the same mechanics, but the bases are now the same. The base function here is delta function. The base function here is imaginary exponential signals. And the connection between these two domains actually is the convolution theory of discrete time Fourier transform. Here is one example. The difference equation for a stable discrete time LTI system is given here. And if the input signal is given as a unilateral exponential signal, what is the system's zero-state response? It's quite straightforward. What we need to do is figure out the system's frequency response and then get the spectrum of the input. Then the zero-state response is the multiplication of the frequency response and the input signal in the frequency domain. And here is the partial fraction decomposition of the zero-state response Fourier transform. And we take the inverse discrete time Fourier transform to get the zero-state response in the time domain. This is another example. Now we have the input. It is a cosine function. What is the system's zero-state response? This is the system's impulse response. We already know that for a cosine function, the output has to be another cosine function. And the cosine function's amplitude and phase will be modified by the amplitude response and the phase response, respectively. So what we can do is quite straightforward. The cosine function with the same frequency, but with modified amplitude and phase. Here is the results. This is how we represent the system in the frequency domain, and this is the zero-state response in the time domain. If we have a periodic input into discrete time LTI system, we can use discrete time Fourier series to help us figure out the system's zero-state response. From the concept of frequency response, we understand the response to the imaginary exponential signal will be the same imaginary exponential signal but modified by the system's frequency response. And we also know that for a periodic signal, it can be decomposed into a linear combination of imaginary exponential signals so that the zero-state response will be the same linear combination of the responses to the imaginary exponential signals. In other words, the zero-state response to periodic signals can be represented by the discrete time Fourier series like this. Here's one example. We have a discrete time LTI system specified by the frequency response here. And this actually is an ideal low-pass filter. And what is the zero-state response to this periodic input? It's a periodic impulse signal. Pay attention to that the period is equal to 16. So the fundamental frequency of the input signal is 2 pi over 16. Compared to the cutoff frequency, we realize that only the DC components and the fundamental frequency components can going through the ideal low-pass filter without any loss. Otherwise, other harmonics cannot go through this system. Now we understand that the zero-state response of the system can be represented by a discrete time Fourier series. So we need to first figure out the Fourier series for the input signal. And that calculation is straightforward. The spectrum for the periodic impulse signal is constant. Now we can try to write out the zero-state response to the periodic impulse signal. Only 3 components can go through the ideal low-pass filter, the DC components and the fundamental frequency components. Now we can simplify to this expression. To summarize, when a periodic sequence is input into a discrete time LTI system, the zero-state response can be represented by a discrete time Fourier transform. And in case a non-periodic sequence is input into the discrete time LTI system, the interaction between the system and the signal can be represented by this equation, and the zero-state response of the system can be calculated using the inverse discrete time Fourier transform. And using the Fourier approach, we can analyze the relationship between the input, output, and the system using a more intuitive way. So that will significantly simplify our analysis of the systems. There are some pros and cons of the frequency approach. So the advantage actually is we can show the change of the signal before and after the system in frequency domain, and it is clear and intuitive. But the shortcomings are also very obvious. First is we can only analyze the zero-state response. We cannot do anything for the zero input response using the current frequency approach. Another limitation is for unstable system because the discrete time Fourier series may not exist, so we cannot use the Fourier approach to analyze that kind of systems. And in the following chapter, we may introduce a new method, Z-transform, help us address these limitations. Thank you.